Okay, so here's a system of equations. We got three equations with three variables. And as you saw in the last video, if you were going to solve this using the elimination method, it can get pretty tedious, especially if you're writing the whole thing down every time. Like if this takes 5 steps to do, for example, five row operations, and you're writing the whole thing down for each row operation, then you're probably writing down the variable x. Let's see, it shows up here 8 times in this system, and if you do that 5 times, you're going to write down the variable x 40 times, and nobody has time for that. So what we're going to do is write this a different way in what's called an augmented matrix. So what we have right here is the system. To write this in augmented matrix form, we're just going to look at the coefficients of x and also the numbers on the other side, but we don't actually need to write down the variable x1, x2, x3, and we'll see why not in a second. So in the first equation here is going to turn into the first row. So that's going to be a 3, -1, and a 1, and there's also a 0. And those go between these parentheses like this. And we're also usually going to write this with a line in the middle, and the line stands for the equal signs here. Okay, so the next equation has a 0 times x1. It's not really written down, but we're going to pretend there's a 0, and we're going to write it there because the first column here is always going to be matched with the coefficients of x1. So that means, getting ahead of ourselves, this is going to end up being an 8 here. So anyways, continuing with this equation to go in this row, we're going to have a 10, 3, and 7. We've got an 8, -pi, square root of 3, and 2/5 for the last one. So whenever you see an augmented matrix like this, just remember that each row stands, it really means an equation behind the scenes, but we're just not writing all that stuff down because it just gets repetitive. So when we write down a system of equation in this form, we can still do the elimination operations that we talked about in the previous video here. We can do scaling, replacements, and swaps. But we are actually just going to refer to these as now row operations. And so when we're doing row operations to an augmented matrix, it still really represents an equation. But instead of saying we're multiplying both sides of an equation in the form of a matrix, that looks like you can multiply a row. And each row stands for a non-zero constant. You can also add a multiple of one row to another row, replacing the second row with a result. And that does not change the solution set of the system of equations that's behind the scenes there. And you can also swap the positions of two rows. Now, to see what this looks like in practice, let's do the exercise from yesterday, except now I'm going to do it as an example for y'all. First thing we're going to do here, you can use this to check your answers too, and you can also see hopefully that the amount of work we're showing, if you really did show all of the steps the same way I was in the previous video, you'll see that this takes up a little bit less space. It's a little bit easier. So what I want to do here is first clear away this 3x here by doing 3 times the first equation plus the second equation here. But first I just need to write it as a matrix. So that's going to be -1x plus 7y equals -7, but we're just going to write a vertical line for that. The 3x plus 10y equals 21. 21. And so there's the matrix, and we're going to write this as a row operation. I'm going to say row 2 is going to be replaced with the sum of 3 times row 1 plus row 2. So row 1 is going to be unchanged here. I'm just doing one thing at a time. Whoops. And we're going to get 3 times negative 1 plus 3 is 0. So that's eliminating the x from this equation. 3 times 7 plus 10 makes 31, plus 3 times negative 7 plus 21 makes 0. And at this point, you can actually see that we've eliminated the y from this. I guess if we eliminated x. So now it just says 31 times y equals 0, which means y equals 0. So I guess you could say y is eliminated too, in a sense, if it is 0. But anyways, let's actually do another scaling operation here to really finish it off. So I'm going to turn this into a 1, so it really just looks like y equals a number. So that's going to be a scaling operation. I'm going to say row 2 is going to be equal to 1/31 of row 2, which gives you that. And actually, now that I have this 1 here, I can do another operation at the same time here, which is a little bit not exactly kosher, but that's okay. I'm going to say after doing this operation, I'm going to say now row 1 is going to be replaced with negative 7 times this new row 2. So that way I'm going to use the new row 2 to clear out the 7 here instead of dealing with the 31. So anyways, that's going to give you negative 1 plus negative 7 times 0 is still negative 1. 7 plus negative 7 times 1 is 0. And negative 7 minus 7 times 0 is still negative 7. And then we can also do another scaling operation. Just say our row 1 is going to be equal to negative 1 times row 1. To make it the same as what it was here, just change this to a plus. And once you have it in this completely finished form, it really does just say that x equals 7 and y equals 0. And that's the solution set is just the set containing that 1.70. Okay, so that's what it looks like if you do everything using row operations. If at this point, if you got to here and you said, okay, x is really equal to 0 because, or sorry, y is equal to 0, because you can see this equation is 31 y equals 0, and then you can just kind of do some reasoning where you don't necessarily need to show the work. But we're going to see why it's useful to be able to formally show this work in a bit when we start. Well, this is actually what we call our reduced echelon form of the matrix, which is useful to have for a lot of reasons. Okay, now let's do the same thing with this one. This matrix is going to have the first row is 1, negative 2, negative 2, negative 27, 0, 1, 3, 35. So that's the original system of equations there, represented as an augmented matrix. Now, if we just want to use row operations instead of like the back substitution, like plugging in 9 for z here, but just using row operations, which is good to get practice with, we're still going to clear away the z column here by doing some row replacement operations, where if I want to clear away this 3, it will be really handy to have all of these zeros here and then a 1 here, because I can make a new row 2 that is equal to negative 3 times row 3 plus row 2. And likewise, you can also make a new row 1, which is going to be equal to, well, I want to cancel out the z in this equation, meaning I'm going to do negative 2z plus 2z. So that means 2 times row 3 plus row 1. So those are the row operations we're going to do here. And that's going to make these become 0. And also notice that because of the fact that we have these zeros here, it leaves these things unchanged. Because, for example, if when we're doing this one, we're doing 2 times row 3 plus row 1. So it's 2 times 0 plus row 1. So that just gives you 0 plus 1. 2 times 0 plus negative 2 is still negative 2. We just managed to, just having the 1 here makes it so you can just clear away the z's and nothing else. But of course I forgot to deal with this stuff here. So we're doing, let's see, negative 3 times 9 is negative 27, plus 35 is 8, and 2 times 9 is 18, plus negative 27 is negative 9. Okay, so now we've eliminated the z's from these equations. The next thing we need to do is just use this 1 to eliminate this negative 2 here. And in order to do that, we just need to do one more row operation, which is going to be replacing row 1 with 2 times row 2 plus row 1, which is going to make this look like, let's see, 2 times 0 plus 1 is still 1. 2 times 1 plus negative 2 is 0. 0 plus 2 times 0 is 0. And 2 times 8 plus negative 9 is 7. So at this point, when you have this in this nice form here where you have mostly 1s and 0s here, it really just means x equals 7, y equals 8, and z equals 9 is what the last equation says, which tells you what the solution set is. Seven, 8, 9, the same reason 6 was afraid of 7. So hopefully you can see it just saves you a little bit of writing to write things in this matrix format. Later on in the class, we're going to look at what do, like just treating a matrix by itself as a mathematical object in its own right, not necessarily standing for a system of equations behind the scenes as well. And row operations will still mean something in that context. So in the next video, we're going to come up with what does it mean formally to have this completely done like this. Like how can we tell there's no more good row operations to do? And it gets a little bit weird when you don't just have one solution, but when you maybe have an infinite number of solutions or no solutions with matrices that or systems of equations that aren't square like this, where you have more equations than there are variables, or more variables than there are equations, and that's going to be called echelon form, what it means to get it so there are no more row operations to be done. So that's the next video. Talk to you then.